Since 2011, the Computer Science Department at UCA has adapted parallel computing into their required courses. Data structure is one of those. So, we want to talk about when you have multiple CPUs, which is true on your computers, cell phones, everywhere. How would you use those multiple CPUs and help you achieve better performances in different problems? So this is the question I want to ask you. Assume you have two CPUs. Assume you know how to use your two CPUs. And you want to add all values in an array. And this array has about 100 elements in there. So of course, you know how to do this in regular C++ programming. You probably know how to do that in your CS1 already. Write a for loop, go through from the first element until the last element, and every time you use array I plus and sums all the values up, which is very simple. But now if you have two CPUs, what will you do? Obviously, you would want to use the first CPU to add up the first half of the elements, and of course, assuming the two CPUs has the same processing powers. The first CPU will sums up all the values of the first 50, and the second CPU will sums up all the values of the second half. But that's of course not the answer of it, because the first CPU has only half of the elements, the other one has the half of the elements. So the CPU2 will need to pass the sum to the first CPU. And this is what we call the communication cost. It will take some time for CPU1 and CPU2 to talk with each other, and then CPU need to sum up all the values. So basically take the sum of the first sum plus the sum passed from the CPU2. And therefore, this is how would we use if we have two CPUs. And by using the same concept, we can, of course, use that idea into the sorting algorithms. So for the merge sort, this might be the perfect example of doing parallel. So of course, if you have multiple CPUs and you want to sort the elements in parallel, merge sort might be even better than the quick sort. So why is that? Because merge sort can easily do the same thing in the whole sequences. Divide that into two. So when you have two CPUs, you do the merge sort on the first half for CPU1. CPU2 will do the merge sort on the second half. And of course, CPU2 then pass the sorted segment to CPU1. Of course, this time the values they need to pass has much more spaces, requires more time to do the communication. Unlike the previous example, just one value. This time we need to pass the whole array. And then CPU1 will need to merge the two segments. So basically this is like a mirror image of what we have seen previously, but the communication cost would be higher. And that's why I'm saying by listening to this one, you know how easy it is to do parallel in merge sort. How about quick sort? Thinking about this. For the quick sort, you need to find a pivot, do the split, and then creating two ideally half segments, and then solve all of the problem recursively. So what's this need to be done? Unlike merge sort, in the very beginning, two CPUs can take their own part and then start doing their work. For quick sort, CPU1 need to process that, the split operation. Hopefully, you can evenly divide the sequence into two halves. So you can pass the second half to CPU2, and then CPU2 can work on that part, and CPU1 can work on the other way of it. And of course, ideally, they would be able to solve their problems coming back and then have the sorted segments. So that is the idea. So in quick sort, it's not as convenient as merge sort. You need to wait for CPU1 to do its own first split operation and then divide the whole sequence into two parts. Of course, if unfortunately the pivot that you choose in the first execution are not a good one. So you will end up with one side of it has much elements, the other one has fewer elements. Then this parallelization won't be as successful as merge sorts. Of course, think about this. We are looking into the case of 2 CPUs. What happens if we have 4 CPUs? So in this case, the first CPU will need to do the work of the split, so divide into 2 parts. CPU 1 will work on the first part, CPU 2 will work on the second part, and CPU 1 work on the first half will be able to divide into 2 parts again, so the CPU 3 can work in as well as the CPU 4 can work in on the second half. So you can see that the structure is there. For quick sort is of course not as powerful as the merge sort. Insertion sort is actually a sorting algorithm that cannot be parallelized. Why is that? Because in the insertion sort, we have one element that need to be sorted out one at a time, so they need to merge into the previous sorted half. And in this case, every step relies on the previous step. So the insertion sort is not able to do the parallelization even if you have multiple CPUs. Shell sort is an interesting idea. Shell sort basically still use the insertion sort, but they try to do unsort operations to deal with different locations, so that you can see if you have 2 CPUs, you can probably say that for the red colors and yellow color, they will handle by CPU 1. For the green, blue, and purple, they will handle by CPU 2. And of course, when they are done, they will need to pass the information. So it relies on how many gap sorts that you have to operate the parallelization. So for shell sort, it is somehow parallelizable. For counting sort, it is pretty easy. For the counting sort, as we mentioned earlier, we need to do the counting and we need to create the additional array based on the range of the values. So in this case, CPU 1 need to create that additional array. CPU 2 will need to do the additional array as well. So CPU 1 will count from the first location until the middle. CPU 2 will count on the second half. And of course, once they have gone through the counting, CPU 2 need to pass that array to CPU 1, and CPU 1 need to sum up all of the values in the 2 arrays and then generate the final result. So counting sort wise is also parallelizable for the multiple CPUs operations. The last one is the radix sort. This is included in your final project. So I want you guys to think about this. How would you parallelize? If you have 2 CPUs, how would you do parallelization on the radix sort? So try to describe it to me. I will also want you to show me a simple example saying that you have 8 elements that you want to use the radix sort. How would you do that when you have multiple CPUs? Finally, let's take a look of what we call an MPI code. So give you a kind of a feeling, how does that going to be possible? So that in the MPI, it is written in C. Notice that it's not C++, it's C. What it will do, including stdio.h, and the MPI is the library to do so. So inside of an MPI code, what you will see is that it will have an MPI initiate as well as an MPI finalize. So that is the block that tells the compiler, indicating whatever happens in between are going to become a parallelized program. So what we will see over here is that inside of it, it will have an MPI communication rank, and it will get an ID. When you try to write the MPI code and when you're executing, it will also require a parameter of how many CPUs that you will use in this program. For example, if I say I need to use 4 CPUs in this MPI code, so when the MPI initiated sees that, it will say, okay, let's start doing the MPI initiate, and I know you would allocate 4 CPUs. So it will go into 4 nodes, reserve the 4 CPUs, and each one will get a rank between 0 to 3. So it's 0, 1, 2, or 3, indicating what is the number of the CPU that you have reserved. And you will also get the total size of the CPUs that it's been using. And therefore, you will know what is your portion that you are supposed to be. Saying that you have 2 CPUs, CPU rank 0 will handle the first half, CPU 1 will handle the second half. And therefore, inside of the code, after you retrieve the rank, you would be able to say that, hey, if CPU rank equals to 0, then you're reading the first half of the array and start doing a merge sort, for example. And if your CPU rank is 1, then you're reading the second half. Of course, if you have 4 CPUs, you will be able to divide it up, the original sequence, into 4 smaller parts. And that's why when you compile the program, and then you just create a file, when you do MPI run, indicating you want to run the program, and then you will say specify how many nodes that you would want, and in this case it's the 4, and then run the program. What's happening is that each processor will get their instructions and they will get their rank. So you can see that there are 4 processors, and then this is a hello world program. So the processor 1 will get, hey, my rank is 0, so I will say process 0 out of 4 processors, 2, 1, and 3. Of course, the order will not follow 0, 1, 2, and 3. Whoever get the communication, get the code done, will output first. And so that the but you would, one thing is for sure is that you will end up with 4 processors doing the hello world program. So that is the idea of how periodization is going to do. The whole purpose of this topic is try to stimulate your interests to want to take periodization, want to take the distributed computing, this kind of things, because it is the future of the computer science.